This video, we will look at the measures of angles and how to classify these angles. To start off with our symbol here, this is the angle symbol we will see typed most often. Again, it looks like a less than sign with an arc going through this. So this would be angle A. And remember, using just one letter is a way to name the angle as long as that letter is the vertex of the angle and there are no other angles present. So when we see this notation, that simply means the name of the angle. When we put the same symbol down, but a lowercase m in front of it, now we are talking about the measure of the angle. In other words, the size of the angle. Because we have angles of various sizes. Some angles you're probably familiar with would be something like 90 degrees, where you've seen a right triangle. But we will have angles of various sizes, and we'll work with those angles. So let's just get used to what we mean by the measure of the angle. I'm going to go ahead and construct an angle over here. So here's our angle with two rays for its sides. We can go ahead and call this angle A to go along with the example over here. So angle A is the picture. It is the object. Now, when we talk about the measure of the angle, essentially what we're talking about is how big of a gap this is. How far apart are these two sides? What's the openness of the angle? So it could be a variety of degree measures. Maybe this one in particular is 60 degrees. And if that's the case, that means that the openness of these two sides is 60 degrees, and that would be the measure of angle A. And so we would show that as the measure of angle A equals 60 degrees. So recall, just like we had different notations for segments, if the bar is above a segment, we're talking about the object. If we take away the bar, we're talking about how long the segment is. We need to use different notations for our angles as well. If it's just the angle symbol, we are talking about the object, the picture. If we put the m in front of it, now we are talking about the measurement of the angle. Okay, so with our angles, we have 4 classifications that we're going to work with. First off here, if an angle has a measure that is between 0 and 90 degrees, so an example of that would be the 60-degree angle we just said. That is what we call acute. So an angle is acute if and only if it has a measure between 0 and 90 degrees. Let's go ahead and add that in. So note that this would exclude a value of 0 and a value of 90, because when we get to a measure of 90, we have a name for that. That is called a right angle. And that is if we're exactly equal to 90 degrees. If we have a measurement that is between 90 and 180 degrees, so not equaling 90 or 180, but somewhere in between those, that is the classification of obtuse. And if an angle equals 180 degrees exactly, that is what we call a straight angle. Okay, and the reason for that is going to be very important. A straight angle is created by 2 opposite rays. And if you remember, opposite rays create a straight line. And so what we need to realize is when we see this straight line, we could think of it as here's one side of our angle going to the right, here's the other side of our angle going to the left, and the openness between these two sides is 180 degrees. And so something very important for us to know is that with any straight line, anytime you are told that you have a line, the angle measure that opens up to that line is 180 degrees. Very useful and very commonly used. So what we need to talk about now is operations that we can use with our angles. Start off with, we're going to talk about the angle addition postulate, which simply says if you have a point in the interior of an angle. So let's look at the big angle shown here. We see there's a third ray going through the middle, going through the interior of it. So let's say on that ray we have a point, and we'll name this particular point R. We can then talk about the interior of the angle. So if we have a point R in the interior of angle PQS. And remember, if we're calling it angle PQS, that would mean that the vertex of this angle is that middle letter Q. And P and S would be on different sides from each other. So maybe we put P on this side and S on this side. So essentially what we're saying is if you have an angle and there is a dividing ray in between it somewhere, making smaller angles in the picture. So we have the big angle PQS, and we also see there's a smaller angle here and here. Then we can use the angle addition postulate, which is just like with the segment addition postulate. It says little angle plus little angle will equal the big angle. So we can see that marked here. When we show little angle measurements, we just write them inside the corners. And when we want to talk about the larger angle in the picture, we use some kind of notation to show that we're talking about the entire span. But it is just like the operations with segments, where we can add two smaller angles that are together if they're making up a larger angle. So in this particular diagram, what we have is the little angle. One little angle is angle PQR, and the other little angle is RQS. So we can say the measure of angle PQR plus measure of angle RQS equals the big angle measure PQS. So some couple things to note here. We can't add pictures together, so we can't add angles together. We can add their measurements together because their measurements are numerical values. So just like with segments, the measures can be equal, the measures can be added. But if the angles are the same size, we do have the same classification there. So if two angles are what we call, again, congruent, just like we did with segments, and let's show that symbol again. So remember this symbol, it looks like an equal sign with a squiggle above, that tilde above it. Two angles are congruent if and only if they have the same measure. Same thing we said with segments. So just like with segments, angles, the actual figures, the picture can be congruent. Their measures can be equal because their measurements are numerical values. So we'll see that a lot, and we'll talk about how to show that with our angles as well. So we can look at that in a diagram like this one. If we want to show that angle A is congruent to angle B, it's kind of similar to what we do with segments, but when we talk about the measurement of the angle, we're talking about the inside portion between the sides of the angle. So to show that angle A is congruent to angle B, what we'll do is we'll put a little arc inside here. And to show that this angle is congruent to that one, just match the number of arcs. So if you put one arc on angle A and you put just one arc on angle B, what we are saying is that these two angles are the same size. And so then we would also know their measurements are equal. So if this angle right here had a measure of 55 degrees, this angle over here, we would automatically know has a measurement of 55 degrees. Okay, so one more piece of vocabulary here before we move on to our example is a bisector. Bi means two, and sect means to cut. So bisector means to cut into two parts. So what we say is a line, array, or a segment. So something that is related to a line bisects an angle if it divides the angle into two congruent parts. So in other words, a line, array, or a segment, all of those are related to a line. If they go through an angle in the middle and bisect, they're going to create two equal measurements, so two congruent angles. They're going to cut the angle in half, in other words. So let's use some of that terminology down here. We have some given information about the picture, and the first thing we should do is figure out what all this means for us. Starting off, we are told in the figure ray KJ and ray KL are opposite rays. So here is KJ starting at K and going through J. KL starts at K and goes through L. Because they are opposite rays, they're going in opposite directions. What that means for us is this is a straight line. And if you remember what we said about the measurement of a straight angle, we now know that this entire span here is 180 degrees. If we need to use that, we will. Something else to note in our instructions is that ray KN bisects angle LKM. So again, read that again. KN is bisecting. KN is cutting in half. What is it cutting in half? This angle. So don't reverse what it said. Read from left to right. The ray KN, so let's see where that's located. Ray KN bisects the angle LKM. So in other words, this green ray right here is bisecting this red angle. So we are cutting this red angle into two congruent smaller angles, and we should denote that by showing one arc in each span there. So now I know that this measurement is equal to this measurement. That is all a bisector does. It cuts an angle into two equal parts. Okay, so for this particular example, we know that the measure of angle LKM, which is the big red angle, has a measurement of 7x minus 5. So because that's a bigger angle with two smaller angles in between, we should show that measurement going across that span. So we can show that the entire span here is 7x minus 5. And now we are given that measure of angle NKM is 3x plus 9. That would be from N to K to M. That would be this angle over here. So the span in here, the measurement in here is 3x plus 9. And for small angle measurements, we can just write them inside. We don't have to put the big swoop to show that span. It's understood. Okay, so that's all the information you were given. Now, the key to geometry here is to think, not just do. Okay, that's the trick to geometry. Don't just do something to do something. So you need to solve. You need to find the measure of LKM. In order to do that, you need to solve for x so that you can substitute it in right here. So a quick thing to do would be, well, you have two measurements. What if I just set them equal? Well, we don't really have a reason to do that. So what we want to avoid is just doing something to do it, but rather think about what is it that we know in the picture. And if you are thinking about it, you'll remember that we have said that these two angles here are congruent, and that means that their measurements are equal. So even though we don't know the exact number, is it 45 degrees? Is it 37 degrees? What we do know is that the measurement is 3x plus 9, so this measurement over here would have to be the same, meaning we can also fill in this space with 3x plus 9. And it is a good idea to fill in your diagrams with things that you know, because then you get a visual of what's going on. And what we can see now is we have a large angle here with two smaller angles inside, and that is how we define angle addition property. We said that a small angle plus another small angle equals the big angle that they make up. And so what we can do here to solve for x then is say that 3x plus 9 plus 3x plus 9 equals 7x minus 5. So here's our equation representing little angle plus little angle equals big angle. Let's go ahead and solve. First, let's simplify the left side. Combine like terms here. 3x plus 9 plus 3x plus 9 will give us 6x plus 18. And in solving, we can subtract 6x on both sides, and we'll get 18 equals x minus 15. Sorry, not 15. I don't know where that came from. This was 7x minus 5 over here. So this is x minus 5. And now when we add 5 to both sides, we're going to get x equals 23, which is great. We found that using properties that we know. But we're also not finished, because we were asked to find the measure of an angle, and that angle was LKM. And LKM was the bigger angle here, and we have the measurement for that is 7x minus 5. All we need to do is substitute our value of 23 into this expression. And so we have measure of angle LKM equals 7 times 23 minus 5, and thus the measure of angle LKM equals 156. So 156 degrees. Okay. So as you go through your examples with angles, pay attention to whether or not you know angles are congruent, see if the angle addition postulate applies, but use those properties as you go. And remember that the angle measure for a straight line is 180 degrees.